Hello, today we're going to go on to section 14.2 of our textbook, which deals with derivatives and integrals of functions. So first of all, let's look at the formal definition. The derivative of a vector function r is defined as dr dt, which equals r prime of t, which equals the limit as h goes to 0 of r of t plus h minus r of t all over h. So most of you probably realize that this looks very much like the definition of a derivative of a single variable function back in Calc 1. Okay, doesn't look much different. Notice though, you're subtracting vectors and then you're dividing it by a scalar. So you're taking the vector, the position vector, r of t plus h minus r of t. So I want to just look at this just a little bit in terms of a picture. Let's let this be a position. This is the curve r of t. All right, and let's just suppose that our object's going in this direction. It's moving along this direction along the curve. And let's suppose that this is r of t right here. And suppose this is r of t plus h right here. Now notice our derivative was defined to be r of t plus h minus r of t divided by h. And yeah, we took the limit as h goes to 0 to get your derivative. Notice this vector right here, the vector from here to here, is r of t plus h minus r of t. Because notice, if I take this vector r of t, notice when you add two vectors, what did you say you did? You would draw the first vector, you would draw the second vector where the first one ends, and your solution starts where the first one starts and ends where the second one ends. So notice this vector right here, this one right here, is the difference of those two vectors, because if you take r of t and then add what I'm contending is r of t plus h minus r of t, as you can see, the r of t's cancel and you get r of t plus h. So this vector right here is the difference of those two. And note, as I let h go to 0, this point approaches this point, and you're getting closer and closer and closer and closer to a vector that's right about here. In other words, as you can see from the picture, the derivative is a tangent vector. It's a vector that's tangent to the curve, just like the derivative gave you the slope of the tangent line before. But this derivative is going to be a derivative, and it's going to be a vector that's tangent to the curve at the point of tangency. Okay, so if I had a curve that looked like this, all right, and I wanted to know at this point right here, maybe this is at t equals 2, and I wanted to know what r prime of 2 looks like. I'm not sure how long that vector r prime of 2 is going to be, but I know that that vector is going to be tangent to the curve. It might be that long, it might be that long, it might be that long, but I know the direction. Or it might even be in this direction, but it will be, if you draw the line through that vector, it will be a tangent line. And that's an important thing to take into consideration. Now, the vector r prime of t actually is called the tangent vector to the curve. Okay? And the tangent line is the line parallel to the vector that passes through the point of tangency. So as I said a few minutes ago, if you had a curve that looks like this, and I wanted to draw my tangent vector, I'm not sure how long it is. We'll do that in a few minutes, how you actually do your computations. But it's going to be tangent to the curve. And if I draw the line that goes through this point and is in the direction of this vector, that line is called your tangent line. It's that easy. It's not all that hard. Now, how do you go about finding the derivative? You do it just like you did back in Calc 1. And they actually have this proof in the book, but I'm not going to worry about doing the proof here. What it says is, let me just put this under here, theorem, if r of t is equal to f of t, g of t, h of t, in other words, these are my components, r prime of t, the vector r prime of t, has as its components the derivative of f, comma, the derivative of g, comma, the derivative of h. So quite simply, when we differentiate vector-valued functions, we differentiate component by component. It's that easy. It's not hard at all. So we also can define one more thing. The unit tangent vector is a vector that's in the exact same direction as the derivative, except we want it to be of length 1 since it's a unit vector. And we all know how you get a vector that's in the same direction but of length 1. You divide it by its length. So we define this tangent vector as the derivative vector Just divide it by its length. That's all we have to do. Okay, and that's called the tangent vector, big T. Note, what's the magnitude of big T at any time? 1. Because since we divided it by its magnitude, we forced it to be a vector of length 1. So now, if I did have a curve that looks like this, and maybe the orientation is I'm going along this way, and I say, oh, draw me the tangent vector right here at this point, I know it's going to be tangent to the curve, and the length of that vector is of length 1. That's big T. All right. Let's do a couple of examples, and these are real simple ones. Suppose r of t is defined to be 1 plus t cubed I plus 3t squared j minus 5tk. To determine r prime of t, life is incredibly good. I look at my I component and I say, what's the derivative of 1 plus t cubed? Oh yeah, it's 3t squared. So it's going to be 3t squared I plus, what's the derivative of my j component? 6t minus, what's my component of my k? 5. And that's it. The derivative of a vector valued function is a vectored value function. Okay, easy, not hard. Determine the unit tangent vector at the point t equals 1. Well, a few minutes ago we figured out that r prime of t was equal to 3t squared I plus 6tj minus 5k. Again, I just differentiate it term by term. So if I wanted to know what's my r prime of 1, in other words, what's my derivative evaluated at t equals 1, all I need to do is plug t equals 1 into each of my x, y, and z components. So I get 3 times 1 squared is 3, 6 times 1 is 6, and a negative 5 by itself is a negative 5. Now recall, the unit tangent is the derivative vector, but to make it of length 1, we divide it by its length. So I want to take the vector, since r prime of 1 was the vector whose components were 3, 6, and negative 5, I need to divide it by its length. And how do we take the length of a vector? It's the square root of the x component squared plus the y component squared plus the z component squared. And let's see, 9 plus 36 is what, 45? And 45 and 25 is 70. So I have 1 over root 70 times 3, 6, negative 5. And that's my unit tangent vector. It's the same direction as r prime of 1, but we fixed it to make it of length 1. So all we have to do is divide it by its length. Okay, not hard. Not hard at all. But this vector is very important, big T. All right, now they want me to determine a representation of the tangent line to the curve at the point determined by t equals 1. Now I really don't have to draw what this curve looks like, but let's just go through what's going on here. You've got some curve, all right, r of t. Now we want to know the tangent line, parametric representation probably, of the tangent line to this curve at t equals 1. Now at t equals 1, notice r of 1 is equal to what point? Let's see, 1 plus 1 cubed is 2. 3 times 1 squared is 3. And 5 times 1 is 5. Right? So r of 1, the position vector that corresponds to t equals 1, is pointing me to the point that's 2, 3, negative 5. So I have a particular point, 2, 3, and let's pretend just for keepers that that point right there is 2, 3, negative 5. Now I need to get the equation of the tangent line. I want the equation of this line. As you well know, to get the equation of of any kind of line, what do we need to do? We need a point. I've got myself a point. And I need a vector that's pointing me in the direction of the line. Well, any suggestions how I can get that vector? Ah, it's the tangent vector, huh? We can use r prime of 1, or we can use big T. To me, figuring out r prime, we did a few minutes ago, r prime of t was 3t squared I plus 6tj minus 5k. So a few minutes ago we figured out that r prime of 1 was 3i plus 6j minus 5k. So I have myself a vector. I have a vector that's pointing me in the direction of that line. That vector that's pointing in the direction of the line has components 3, 6, negative 5. So back with the old x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. My particular point, my x naught, y naught, z naught, my point on the line is the point 2, 3, negative 5. And my vector, whose components are a, b, c, that's parallel to the line, is this vector 3, 6, negative 5. Notice I could have used the unit tangent, but why do I want to throw in that 1 over root 70? You know, that's sort of complicated. I just need a vector in the direction of the line. So these numbers are easier. I'll use 3, 6, negative 5. So plugging in, I get my equation to be, let's see, x equals, x naught is 2 plus 3 times t. Y equals, y naught is 3 plus 6 times t. And z equals, my z coordinate is a negative 5 minus 5 times t. And that is a parametric representation of my tangent line. Is it a unique representation? Absolutely not, because we just had to get a point and a vector pointing me in the direction of the line. Or as your book says, a vector parallel to the line. And your tangent, your derivative, your tangent vector always is parallel to the line. Okay, any questions? Nope, not hard. This is a pleasant section. Okay, well, let's go back and review a little bit. Oh, now remember, one thing that we learned here is if you have a curve, and I'm just drawing it in 2D because it's easier to do it, at any point, if I wanted to draw the tangent vector, I know it's tangent to the curve. I don't know how long it is. Like this point right here, the tangent vector would be going like this way, would be going this way, as long as the orientation as t increases is going along this way. Okay, now in this one, this is from your homework from the other night, we say sketch the curve whose components are cosine t, comma, sine t, comma, t. All right, so let's go back and sketch this. I think most of you would notice, first of all, you go, oh, Miss Strocko, let's see. If I look here, x is cosine t, and y is sine t. So since I know that cosine of t squared plus sine of t squared is 1, I have x squared plus y squared is 1. So I know all the points that satisfy this equation, which you can think of it as x, y, z coordinates. The x, y coordinates satisfy this equation, x squared plus y squared equals 1. In other words, if I plot x and then y next, it's always going to fall on the circle, whose equation is x squared plus y squared is 1. This circle's centers the origin, and its radius is 1. So what I'm going to do right here is I'm going to draw myself a little circle that's of radius 1. Now notice my x, y coordinates satisfied this equation. So if I plot x, and then if I plot y, before I go up z, I'm on the circle. So whenever you go up z, you could go up z some amount, or yeah, you could go down z some amount, but your points are going to have to be on this cylinder, because every time you plot x and y, I don't know if you go x back, you're going to have to go up or down z. Think of those as parallels through that circle, perpendicular to the xy plane when you go up z or down z. Now let's plot some points here though. Let's see. If I let t be 0, let's just get a couple points here. My first point is cosine of 0, which is 1, sine of 0, which is 0, and t is 0. So 1, 0, 0 is right here. Let's do it in red. Okay, now if I let t be pi over 2, and note that pi over 2 is about what, 1.57 approximately. My point there is going to be cosine of pi over 2. Cosine of pi over 2 is, what's cosine of pi over 2? 0. Sine of pi over 2 is 1. And then z is pi over 2, but it might be easier to think of that as 0, 1, 1.57. So if I plot 0 in the x direction, 1 in the y direction, and up 1.57, right about there I am. Let's let t be pi. Now notice your z coordinate is pi, so as as you're going around that circle, the z, which is t, is lifting you higher and higher above the xy plane. Plotting this in, let's see. Cosine of pi is what, a -1? Sine of pi is, what's sine of pi? 0. And t is pi. I'm going to call that 3.14. So let's see, if you're doing x is a -1, y is 0, and we're going up pi, my point's right about there as I go dot, 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 up to there. Notice so far, as our t, which is z, increases, we're going higher, higher, higher. Let me do another one. T equals 3 pi over 2. What's the cosine of 3 pi over 2? 0. The sine of 3 pi over 2 is a -1. And 3 pi over 2, what's that, about 4.7? So if x is 0, y, now let's see, we went 0, 1. We were at 0, 1, pi over 2 is here. Then we went, x was a -1. Y was 0, up 3 pi over 4. Now x is 0, y is a -1, and then we're going up to 4.7. So I'm thinking if this much is 1 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, we're going to be about here. So it's wrapping it around to here. And as you can see what's happening, in fact, let's just do 2 pi, and then we'll quit. If t is 2 pi, cosine of 2 pi is 1. Sine of 2 pi is 0. And 2 pi is about 6.28. So if we're back to 1, 0, go in the x direction 1, in the z direction 0, and this one in fact was right here, so it should be, we're going to go all the way up to here till about here, and this is wrapping around. So what's happening is this thing's wrapping around and we're going higher, and as you can sort of think as, make a little picture right here for you. If this is your xy, and your xy coordinates have to satisfy this circle equal to 0, so your cosine t, sine t, t, these guys are making you go around the circle, but each time as your t gets higher, you're going higher and higher and always wrapping around, but going up, going around that cylinder. So this is what our curve looks like. It's wrapping around the cylinder, x squared plus y squared equals 1, and we get it higher and higher. They call this a lot of times a helix. Okay? Now, for part B, I just want to show you how we're going to fudge it a little bit. Draw the position vector of the point that corresponds to t equals pi, which is r of pi. All right? Well, we figured out r of pi was x was a -1, y was 0. Right here was r of pi. So my position vector goes from the origin to that point. That's r of pi. R of pi is the vector that points you from the origin to that point. Okay? So like r of 0 would be this vector right here. R of pi over 2 would be that vector right there. Okay, now in part 3, they want me to sketch r prime of pi. Now I don't want you to go through and try to draw r prime of pi from here, but I want you to realize is the orientation is I'm going in this direction. So I can tell you what r prime of pi is going to go. R prime of pi is going to be tangent to the curve. I don't know the length, but it's going to be going in that direction. So r prime of pi looks like that. I don't expect you to go evaluate r prime of pi and then try to draw a vector from this point with the certain components that you have, because it'll be next to impossible to draw it. But you should realize that the tangent vector is tangent to the curve, and it points you in the direction of the motion as t is increasing. Notice we were going this way. Okay, so that's all you needed to do for that one, just to sketch it. Okay, a couple more things. In your textbook in 14.2, they actually derive some of these and others, they just hand them to you as a silver platter. But they have differentiation rules for the sum of two vector-valued functions, a scalar times a vector-valued function, a scalar function times a vector-valued function. And we're not going to go about and prove them. You can prove them starting with that definition that we had at the very, very beginning of class using this. You can prove them using the definition. And the proofs, believe it or not, look identical to the proofs that when you prove these back in Calc 1. It's just that you have a little cap to make it a vector over R. Notice, we just want to review them. If you have the sum of two vector-valued functions, all you have to do is take the derivative of the first plus the derivative of the second. And remember, if I wanted to add two vectors and they were in component form, you know, you just add your x components, add your y components, add your z components. If you have a scalar times a vector-valued function, same thing as in Calc 1. It's the scalar times the derivative. And this one's cute. If you have a scalar function times a vector function, you go, what would that look like, Mrs. Strocko? Well, let me show you what it would look like. Suppose I had t squared plus t times the vector value function t comma t cubed comma t to the fourth. This is a scalar function times a vector function. Now, you could take t squared plus 2 and multiply it times each of those, and then take the derivative of each one separately. Or you could use this lovely rule, which says the derivative of f prime times u of t plus f of t times the derivative of u prime, or the derivative of u, which we write as u prime. Doesn't that look just like the product rule that we had back in Calc 1? Yeah, it's the same thing. We have three more rules. This is dot product. Dot product. Okay. The dot product, if you want to differentiate the dot product of two vectors, you could take the dot product first and then differentiate, or you can prove that it's equal to the derivative of the first function, dot it with the second, plus the first function times the derivative of the second. Okay, and if you write it out, you can prove it. I mean, it's not too hard to do. Now, if you want to differentiate, now notice, when you differentiate a dot product, you have a scalar function. So this better turn out to be a scalar. You also you can talk about the derivative of the cross product of two vectors, and it looks just like the product formula, u prime cross v plus u cross v prime. And lastly, we have a chain rule. If you have u of f of t, notice f of t is a scalar, it's equal to u prime of f of t times f prime of t. Okay? So we're not going to go bother proving these. If you look in your textbook, they go through and do them, but they're nice ones to know. Let me show you one little thing, though, that I like a lot. Notice this one. This one, differentiating the dot product of two vectors. It's the derivative of the first times the second plus the first times the derivative of the second. There's a little lemma I want to show you that's sort of a neat little thing to do. Look at this lemma. Suppose the magnitude of r of t is equal to a constant. And let's call that constant k. All right? So the length of r of t is a constant. Well, what if the length of t, the length of r of t, the magnitude of r of t is a constant? What is that telling me? In particular, let's do it in particular. Let's do it in particular. Let's say in particular, let's say the magnitude of r of t is 5. What does that tell you about the graph of r of t? If its magnitude is always 5, what does that tell me where I am? What the graph would look like? Can you tell me anything about the graph? If the magnitude of r of t is always 5, your position vector is always 5 units long. So your point's always 5 units from the origin. Well, if you're always 5 units from the origin, you've got to be lying on the sphere whose radius is 5. So if r of t is 5, I have no idea what r of t looks like. But if I drew a sphere, and you know my spheres really aren't the best spheres in the world, but if I drew a sphere of radius 5, I have no idea what r of t looks like. But it's moving along somehow. Who knows what it's doing? But it's on the surface of the sphere. Okay? In other words, r of t lies on the sphere whose center's the origin and whose radius is r. Now there's something even cooler that we can derive, though. Let me show you what we can cool. Watch this. Vector r of t, all right, has an x component, a y component, and a z component, right? Do you all agree that the magnitude of r is the square root of x squared plus y squared plus z squared? Okay. What is r dot r? Well, that would be x times x, which is x squared, plus y times y, which is y squared, plus z times z, which is z squared, which equals the magnitude of r squared. So in other words, r dot r is the magnitude of r squared, and we supposed in particular the magnitude of r was 5, so it would be 5 squared, which is 25. Okay? All right. Any vector dotted with itself is what you will get is its length squared. Now guys, what I'm going to do is I'm going to differentiate both sides. Using the product rule that we had a few minutes ago, the derivative of this baby cakes is going to be r prime dotted with r plus r dotted with r prime. What's the derivative of 25? 0. Dot product is commutative, right? A dot b is the same as b dot a. So this is 2 times r dot r prime. If I divide by a 2 on both sides, r dot r prime is 0. Who can remember from chapter 13? If the dot product of two vectors is 0, what do you know about the two vectors? They're perpendicular, right? Because remember when you took the dot product of two vectors, a dot b, it was the length of a times the length of b times the cosine of the angle. If the cosine of the angle is 0, the angle's got to be 90 degrees. Aha! So r is perpendicular to r prime. Now, let me do this drawing in 2D instead of 3D. If the magnitude of r is a constant, in particular, if the magnitude of r is 5, we said in 3D I've got to be lying on the sphere. In 2D I'd be lying on a circle. A circle of radius 5. And what we have just proven is if you pick any point at all and you draw a position vector, there's my position vector, r of t, and you draw the tangent vector, the angle between them is 90 degrees. Okay? That is if the magnitude of r is a constant. So if you're moving along a circle, at all times the tangent vector and the position vector form a 90-degree angle. And if I could draw it in a sphere, it's the same thing. In other words, the tangent vector is always perpendicular. Those of you that took geometry, do you remember when you learned in geometry, if you had a circle and you draw a line segment from the center to any point, the tangent line is always perpendicular to the radius? Yeah, it's the exact same concept. Okay, we just sort of proved it this time is what we did. Okay, we've got a couple more things to go over, not much though. Next, how do you integrate a vector-valued function? Piece of cake. To integrate a vector-valued function, what we need to do is integrate each component, term by term. Easy. I just threw this in. We're not really using it today, but we will use it later. A curve r of t is called smooth if r prime is continuous and if r prime is never identically equal to 0. In other words, every tangent vector has a little bit of a length to it. Okay, it doesn't disappear to 0. Except possibly at the endpoints. Like if you're talking about like from t equals 0 to t equals 10 on the interval, it could be, r prime could be 0 just at the endpoints. Okay, a couple things we've got to do. Let's go over them. Simple little problem right here. The reason I threw this in is some of us are Calc 1's a little bit rusty, so I thought it might be a good idea to go over these. If vector r of t is sine of 2t, comma, cosine of 3t, comma, e of 2t, determine r prime of t. Quite simply, all we have to do is differentiate term by term. Last time I looked, derivative of sine u was cosine u, so derivative of sine 2t is cosine of 2t, but then we have to multiply times 2. Derivative of cosine u is minus sine u, so it's minus sine 3t, but then we have to multiply by 3, the derivative of 3t. And lastly, the derivative of e to the u is e to the u, but then you have to multiply times the derivative of u, which is t. So I brought this one up just because if it's been a while since you had Calc 2, be sure when you differentiate each of those, you don't forget multiply times the derivative of what's inside. Okay? We don't want you to lose points on a test for that. All right. Let's review a little bit, a couple more. Determine the unit tangent vector t of t at t equals 1. Now notice r prime of t has components. Derivative of 3t squared is 6t. Derivative of t cubed is 3t squared. Derivative of t is 1. The tangent vector at t equals 1 has components 6, 3, 1, because I plugged in t equals 1 in each of those places. But to get the unit vector at 1, we have to take the regular tangent vector and divide it by its, that should be a prime there, I apologize, and divide it by its length. So we've got to take 6, 3, 1 and divide it by square root of 36, which is 6 squared, plus 3 squared, which is 9, plus 1 squared, which is 1. And that gives me, let's see, 36 plus 10, 1 over root 46 times the vector 6, 3, 1. And that's my answer. Notice this vector goes in the exact same direction as r prime, but it's of length 1. It's a vector of length 1. Okay. Determine a set of parametric equations for the tangent line to the curve at the specified point. We did this a few minutes ago, but let's just do it again. I think one more example would be good before you start doing your homework. Notice this is a curve. We have some curve here. There's some point. The point is negative 1, 1, 1. They're giving me negative 1, 1, 1. And we want to get the equation of the tangent line through that point. To get the equation of any line, we need a couple things. We need a point. They gave me the point, negative 1, 1. And we need a vector parallel to the line at that point. How do you think we're going to get the vector? Well, notice this equation we could write as r of t is equal to the x component's t squared minus 1, the y component is t squared plus 1, and the z component is t plus 1. So if I wanted to take the derivative, I would get 2t, comma 2t, comma 1. Okay. Now the problem is, to get the vector that's pointing me in this direction, I have to know to what plug t in for. And they just gave me the point, negative 1, 1, 1, but they didn't tell me what t they were plugging in. So I look back at my original equations, and I go, wow, what t did they use to get that point? Well, whatever t they used, t squared minus 1, the x equation, turned out to be a negative 1. The y became to be 1, and the z became 1. What does it look like they're letting t be?
0.
Absolutely. That point corresponds to t equals 0. Many times you have a little bit more calculations to do than this, but you know, I take the easier one, the bottom. T plus 1 equals 0 equals 1. Yeah, t equals 0. Yep, it works for all the others. So that corresponds to t equals 0. So my vector that's pointing me in the direction of the line corresponds to the derivative evaluated at 0, which gives me components 0, 0, 1. So that is my A, B, C. So my vector has components 0, 0, 1. This is my A, B, C. This is my x naught, y naught, z naught. So now to do my equation, I know it's going to be in the form of x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. So I'm going to get x equals negative 1 plus 0 times t, y write it. Y equals 1 plus 0 times t, y write it. Z equals 1 plus c, which is 1 times t. There are my parametric equations for the line that's tangent to the curve at the point negative 1, 1. So often they'll give you the point and they don't tell you what the parameter is. You have to do a little bit of algebra to figure out what that parameter is that corresponds to that point. And you will find sometimes your curve could look like this. You know, it could come around and loop-de-loop. You might have multiple t's giving you that point. You know, like I might end up at t equals 5, I'm here, and I loop around and maybe t equals 10, I'm back here. Okay, so that can drive you a little bit bonkers sometimes. Okay, moving right along. Let's see what else we have. Let's see. This is all plain paper. Next one. Evaluate the integral from 0 to 1 of the vector valued function 4 over 1 plus t squared j plus 2t over 1 plus t squared k. And as we know from our definition, this is equal to the integral from 0 to 1 of 4 over 1 plus t squared dt times j plus the integral from 0 to 1 of 2t over 1 plus t squared dt times k. All right, now the reason I picked those two is some of us, our integration techniques might be a little bit shaky. So the first one I need to figure out is this one. What's the integral from 0 to 1 of 4 over 1 plus t squared dt? First, I'm going to just factor out the 4. You are allowed to use the integral tables in the front and flat back of your book. If you have a TI 89, you can use it. If you want to use Maple, you can use it. Who can tell me what is the integral of 1 over 1 plus t squared dt? Arctan. This is arctan. And we're evaluating it from 0 to 1. So this is 4 arctan of 1 minus arctan of 0. Arctan of 1 is find me the angle whose tangent is 1. That's pi over 4. Find me the angle whose tangent is 0. That's 0. The 4's cancel, and we get pi. So that first integral turns out to be pi. All right, so this is going to equal pi times j. Now we have to figure out what's that integral. So let me get a fresh sheet of paper. And now I want to figure out what's the integral from 0 to 1 of 2t over 1 plus t squared dt. I think I want, for this one, I think I'm going to use substitution. I think I'll let u equal my denominator. If I let u equal 1 plus t squared, notice du is 2t dt. So this is equal to the integral of 1 over 1 plus t squared times 2t dt, which, and that's from 0 to 1. Integral from, now 1 over 1 plus t squared is 1 over u, and notice your 2t dt is your du. Now notice I'm not going to put my limits of integration here. I could if I want to, but if I do that, I have to put what u is ranging from, which we can do it that way if you want. Notice, since u equals 1 plus t squared, when t is 0, notice u is 1 plus 0 squared, which is 1. And notice when t is 1, u is 1 plus 1 squared, which is 2. So as t is ranging from 0 to 1, if I want to do my integration in terms of u, when t is 0, u is 1, and when t is 1, u is 2. This is as u ranges from 1 to 2. We can do it that way. And the integral of 1 over u to u last time I looked is log absolute value u, and we're going from u equals 1 to u equals 2, which is natural log of 2 minus natural log of 1. Does anybody remember what the natural log of 1 is? 0. So this is natural log of 2. So my last integral is natural log of 2. So here I'll put plus natural log of 2j. And so what can make these difficult is we have to remember how to do an integral. Okay? All right. Last one. If r of t, find r of t if r prime of t is equal to t squared I plus 4t cubed j minus t squared k, and r of 0 is j. Now they're telling me r of 0 is j. Notice j is the vector whose x component is 0, y component is 1, z component is 0. So they're telling me if I evaluate this vector valued function at 0, I just get 0, 1, 0. In addition, they're telling me that r prime of t, and I'm just going to write it as a vector if you don't mind. T squared is the x component. 4t cubed is the y component, and minus t squared is the z component. Now back in your Calc 1 days, if I had, if I told you f prime of t was 2t squared, and let's say f of 0 is 5. Back in your Calc 1 days, if you wanted to find out what f of t was, what would you do?
Integrate.
I think you would integrate. You would integrate this side and integrate that side, and you get f of t, in this case, is 2/3 t cubed plus a constant, right? Back in your Calc 1 days. And since f of 0 was 5, you go, oh, Ms. Strocko, since f of 0 is 5, if I plug a 0 in here, I get 0 plus c. That tells me c is 5. So my function is f of t is 2/3 t cubed plus 5. You remember doing those. You did them in Calc 1, you did them in Calc 2, right? All right, now the problem is here. R prime of t is t squared, comma, 4t cubed, comma, minus t squared. So to me figure out what r of t is, I'm going to integrate both sides. Just be careful. When I integrate this side, I get r of t. When I integrate this side, I have to integrate this one, and this one individually. You with me? So I will get the vector now. If I integrate t squared, what do I get? 1/3 t cubed plus some constant, right? Because it's an indefinite integral. The second one, if I integrate 4t cubed, I get t to the 4th plus some other constant, which I'm going to call c2, because nobody knows for sure if c1 and c2 are the same. And if I integrate the third one, I get minus 1/3 t cubed plus some other constant. So we have to find out what are c1, c2, and c3. But they told me r of 0, which if I plug a 0 in for t here, I get c1, comma, c2, comma, c3. They told me r of 0 is the vector 0, 1, 0, which tells me therefore c1 equals 0, c2 equals 1, and c3 equals 0. So I can take those values, plug them back up, and I get r of t is equal to, let's see, c1 was 0, so that just gives me an x component of 1/3 t cubed. They tell me c2 is 1, so that'll be t to the 4th plus 1. And c3 was 0, so I'll just have minus 1/3 t cubed. And I'm finished. I have found a vector whose derivative is what they told me, but who r of 0 gives me the unit vector j. Okay, this section's not too tough. So for homework, what I want you to do is look over pages 892 to 896. And then you need to do on pages 897 to 898, numbers 9 through 13, the odds, 17, 19, 23, 25, 33, and 35. And again, remember, you do have the Student Solutions Manual. You're supposed to use that. But if you use it and you're looking at it and you're quite befuddled and you're thinking, how did they get that answer? What possessed them? Email me, leave a voicemail, and I'll post it on the Blackboard site. I'll write it out in my handwriting and explain how to do it. Okay, see you next time.